Good morning, ladies and gentlemen, and welcome to the second visual lecture of Physical Chemistry 321. For today's lesson, we are going to look at different factors that can affect the equilibrium conditions. Okay, first of all, let us not forget that we said that when we talk about the equilibrium is a state that will be reached when the rate of the forward reaction is equivalent to the rate of the backwards equations. There are a number of factors that can affect these conditions. So these factors, they also include like temperature, they also include pressure, and they can also include the presence of a catalyst. The question that we want to answer is that what effect will a change in temperature, will a change in pressure, or the presence of a catalyst will have on the equilibrium position? So let's start with the first fact. Let's start and let's see what the presence of a catalyst will have on the equilibrium conditions. By definition, we know that when we talk about a catalyst is a substance that can speed up the rate of a reaction without necessarily being consumed in the reaction. How does a catalyst work, people? A catalyst, it normally provides a different pathway with a lower activation energy, and it will also assist the reaction to reach completion fast. So if we are having a reaction that will take 10 hours to reach completion, so in the presence of a catalyst, the very same reaction, maybe it can take 5 hours to reach completion. So if we are calculating the reaction Gibbs energy of a reaction before the presence of a catalyst and also after the presence of a catalyst, it has been found that the reaction Gibbs energy will be unchanged. So even the equilibrium constant will also be unchanged. So in other words, we are saying that the presence of a catalyst in a reaction does not have any impact on the reaction Gibbs energy, or does not have any impact on the equilibrium constant. How about a change in temperature, or how about a change in pressure? Okay, for the effect of temperature, let us see that what impact will the effect of temperature have on the reaction Gibbs energy. But for in these instances, I want to look at three different scenarios. One, we can have a scenario whereby we're having fewer moles of gases that are produced with increasing temperature. And we can also have a scenario whereby there is no net change in the number of moles of our reaction. And we can also have a scenario which produces more moles of gases with increasing temperature. Okay, for the first scenario, I think when we look at our graph, we are actually looking at the bluish graph. As we can see from that particular graph, that particular graph is actually it's actually increasing with increasing the temperature of our system. So for that reaction, we have 1 mole of carbon monoxide plus 1/2 oxygen. That will give us 1 carbon dioxide. From that reaction, when we look at it, so when we can calculate the total number of moles of the reactants, it will be 3/2 or 1.5. And the total number of moles of the product is only 1. We can see that for that reaction, the very same reaction, it produces fewer number of moles. Okay, for this kind of reaction that produces fewer number of moles, it normally increases with increasing temperature. Okay, the second instance is whereby we don't have any change in terms of the number of moles. So when you look at the brownish graph, I think we can see that with increasing temperature, our graph remains constant. We have 1 over 2 carbon, which is in the solid state, plus 1 over 2 oxygen, which is in the gaseous state. And the product is 1 over 2 carbon dioxide. So when we calculate the total number of moles, we normally omit the number of moles from the solid state as well as the liquid state. In terms of the gaseous state, we can see that we have 1 over 2 oxygen, 1 over 2 oxygen, and also have 1 over 2 carbon dioxide. So in this instance, we can see that there is no change in terms of the number of moles. Even for this reaction, if there is no change, it means that the reaction Gibbs energy will also not change. Okay, the last scenario, the reaction Gibbs energy of a reaction that produces more moles of gas, it decreases with increasing temperature. So when we look at the reddish graph, from the reddish graph, we can see that the graph is decreasing. So let's look at the number of moles. The reaction is carbon plus 1 over 2 oxygen, that gives us carbon dioxide. So looking at this reaction, you can see that the total number of moles of the reactant is 1 over 2 for the reactant, because we are omitting the number of moles for the solid substances. And the total number of moles of the product, it is just 1. As we can see that 1 is greater than 1 over 2. Therefore, this kind of reaction will decrease with increasing temperature. So in summary, we can see that for the effect of temperature, what is important is the number of moles. If the number of moles are not changing, the reaction Gibbs energy is also not going to change. If the number of moles, more number of moles are produced on the side of the product, it means our graph is going to increase. But if the number of moles will decrease, it means even our graph will also decrease. So in a nutshell, there is a principle that governed like all these things. So this principle is commonly known as Le Chatelier principle. And Le Chatelier principle suggests that when a system at equilibrium is compressed to the composition of a gas phase equilibrium, it adjusts so as to reduce the number of molecules in the gas phase. Okay, ladies and gentlemen, let's move forward. So when we move forward, we want to look at the effect of pressure on the equilibrium conditions. A change in pressure, it does not change the value of equilibrium constant, but it does have other consequences like on the composition. So I think you can read through in the textbook around this particular one. However, what is important about this statement as well as this graph is that a change in pressure does not change the value of K. I want you to look in terms of your textbook and see what other consequences have the value of K it has on the equilibrium conditions. So as we are trying to summarize this particular lesson as well as lesson number 1, let us not forget that we started with the reaction Gibbs energy. The reaction Gibbs energy whereby the slope of a plot of a Gibbs energy against composition. The most important thing about the reaction Gibbs energy is that we are going to predict whether are we going to have a spontaneous reaction or we are not going to have a spontaneous reaction. So even if we are going to have a spontaneous reaction, in which side? Are we going to have a forward spontaneous reaction or are we going to have a backwards spontaneous reaction? Secondly, we said that the condition of a chemical equilibrium at constant temperature and pressure is delta Rg is equals to 0. I think this one, I've actually talked about it in details during lesson number 1. And the other thing, when we're having a reactant, we said that we can have like the linear of Q or K, or the linear of Q or the linear of K, depending on what are we working with. So if you are working with the concentration, it means we're going to have equilibrium constant. In that instance, we're going to have K. But if you are working with the pressures, it means we're going to have Q. And the ln of Q, it can be related with the reaction Gibbs energy according to that reaction. But in the case whereby we are having the equilibrium constant will be related to the reaction Gibbs energy according to Rg is equals to minus RT, the ln of K. So if you are having that particular statement, it means that if we know the value of reaction Gibbs energy, we can calculate the value of K. Or if the conditions are given of K, it means we can be able to calculate the value of the reaction Gibbs energy. Let us not forget that R is a constant and the temperature in this case will be at constant and it will be provided to you. And lastly, we also said that a compound is thermodynamically stable with respect to its element if the delta Fg is less than 0. And for this lesson, we said that the equilibrium constant of a reaction is dependent on the presence of a catalyst and independent on the of pressure. We saw that the presence of a catalyst does not have any impact on the equilibrium constant and as well as the reaction Gibbs energy. So with this particular slide, ladies and gentlemen, I think we are done with this particular lesson. So till we meet again, thank you.